Welcome back. I'm Professor Ayman Alzaid, and in this lecture, Lecture 4.2, we focus on Objective 1 through 5, interpreting set builder notation. This is one of the most important and widely used notations in mathematics and computer science, so let's make sure you truly understand it. By the end of this lecture, you should be able to read and pronounce set builder notation correctly. Identify the three components, the variable, the domain, and the condition. Convert between roster notation and set builder notation in both directions. Evaluate whether a specific element satisfies a set builder condition. Write your own sets using set builder notation. These skills directly support Objective 1 through 5 and will appear on Module 1 homework and the Module 1 quiz. Before we define set builder notation formally, let's understand why we need it. Roster notation works fine for small sets. But what about the set of all even integers, or the set of all real numbers between 0 and 1? We cannot list those, there are infinitely many. That's where set builder notation shines. It lets us describe any set, no matter how large or complex, by stating the property its elements must satisfy. This is exactly how SQL work clauses work in databases, how list comprehensions work in Python, and how type systems in programming languages define valid values. Set builder notation is everywhere in computer science. Let's break down the structure carefully. A set builder expression has three required parts. First, the variable. Typically x, it represents a generic element we are testing. And the domain, written after the membership symbol, this specifies the universe we are drawing from. The integers, the reals, the naturals, or any defined set. This part is not optional. Third, the condition written after the vertical bar. This is the property x must satisfy to be included in the set. The full expression reads, the set of all x in D such that p of x is true. Memorize this structure. The set of x in D such that p of x. It will appear in every set theory topic in this course. The vertical bar is the key symbol in set builder notation. It reads such that. Some textbooks and professors use a colon instead. Both are equally acceptable and mean exactly the same thing. Let's practice reading a full expression. Consider the set of x in the natural numbers such that x is less than 5. Read this aloud. The set of all x in the natural numbers such that x is less than 5. To find the roster form, we test 0, 1, 2, 3, 4 all satisfy x less than 5 in the naturals. The number 5 itself does not, because the condition is strictly less than. So the set equals the set containing 0, 1, 2, 3, 4. Notice the precision required. Less than versus less than or equal to gives a completely different set. Precision is everything in mathematics. Let's work through 4 examples going from set builder to roster form. Example 1. The set of x in the integers such that x is greater than 0. Domain is integers. Condition, x must be positive. Roster form 1, 2, 3, 4, 5, and so on. Example 2. The set of x in the reals such that x is between 0 and 1 inclusive. Domain is reals. Condition, x between 0 and 1 inclusive. This is the closed interval from 0 to 1, uncountably infinite, so roster form is impossible. Example 3. The set of x in the naturals such that x is even. Domain is naturals. Condition, divisible by 2. Roster form 0, 2, 4, 6, 8, and so on. Example 4. The set of x in the integers such that x squared is less than 10. Domain is integers. Condition, x squared must be less than 10. Test carefully. 3 squared equals 9, which is less than 10, passes. 4 squared equals 16, which is greater than 10, fails. Also test negatives. Negative 3 squared equals 9, passes. Negative 4 squared equals 16, fails. Roster form. Negative 3, negative 2, negative 1, do 1, 2, 3. Now let's go the other direction, converting from roster notation to set builder notation. The strategy has 3 steps. Identify the pattern, choose the appropriate domain, and write the condition. Example 1, the set containing 2, 4, 6, 8, 10. Pattern. Even positive integers up to 10. Set builder. The set of x in the positive integers such that x is even and x is at most 10. Example 2, the set containing 1, 4, 9, 16, 25, and so on. Pattern. Perfect squares. Set builder. The set of x in the naturals such that x equals n squared for some natural number n. Example 3. All even integers including negatives. Pattern. All even integers. Set builder. The set of x in the integers such that x equals 2k for some integer k. Example 4. The set containing 1, 1/2, 1/3, 1/4, and so on. Pattern. Unit fractions. Set builder. The set of x in the rationals such that x equals 1 over n for some positive integer n. Practice this conversion skill. It will appear directly on Module 1 homework and the quiz. Now let's apply the notation to test whether specific elements belong to a set. Let A equal the set of x in the integers such that x squared is at most 16. For each candidate, follow 2 steps. First, check the domain. Is it an integer? Then evaluate the condition. X equals 3. Is 3 an integer? Yes. Is 3 squared at most 16? 9 is at most 16, so 3 is an element of A. X equals negative 4. Is negative 4 an integer? Yes. Is negative 4 squared at most 16? 16, 16, 16, so 16. So negative 4 is an element of A. X equals 5. Is 5 an integer? Yes. Is 5 squared at most 16? 25 is greater than 16, false, so 5 is not an element of A. X equals 0. Is 0 an integer? Yes. Is 0 squared at most 16? 0 is at most 16, so 0 is an element of A. X equals negative 5. Is negative 5 an integer? Yes. Is negative 5 squared at most 16? 25 is greater than 16, false. So negative 5 is not an element of A. X equals 2. 5. Is 2. 5 an integer? No. Domain check fails immediately. So 2, 5 is not an element of A. The full set in roster form. A equals the set of all integers from negative 4 to 4. Let me highlight 3 common mistakes students make with set builder notation. Mistake 1, missing domain. Writing the set of x such that x is greater than 0 without specifying where x comes from. Is it from the integers, the reals, the rationals? Without the domain, this set is ambiguous and mathematically incorrect. Always write the set of x in the integers such that x is greater than 0. Mistake 2, overcomplicating finite sets. If you want the set containing 2 and 3, just write the set containing 2 and 3. Set builder notation is designed for infinite or complex sets, not simple finite ones. Mistake 3, impossible conditions. Writing the set of x in the reals such that x squared equals -1. No real number has a negative square, so this set equals the empty set. Always verify that your condition can actually be satisfied by at least one element in your domain. Let's summarize the 5 key takeaways from this lecture. 1. Set builder notation describes sets by a property, not by listing elements. This is essential for infinite or complex sets. 2. The general form is the set of x in D such that P of x, variable, domain, and condition. All 3 parts are required. 3. The vertical bar or colon reads such that it separates the variable declaration from the condition. 4. To test membership, always check the domain first, then evaluate the condition with the given value. 5. Always specify the domain. Without it, the set is ambiguous and mathematically incomplete. Master the form, the set of x in D such that P of x, and you will be equipped to describe, read, and work with any set in this course. Congratulations on completing Lecture 4. 2. Set builder notation. In our next lecture, we will cover subsets, objective 1 through 3, where you will learn to determine whether every element of one set also belongs to another and the difference between a subset and a proper subset. Before then, here is your practice challenge. Convert these 2 sets into set builder notation using the full form. First set, 3, 6, 9, 12, and so on, the positive multiples of 3. Second set, 1, 3, 5, 7, 9, the odd single digits. Write both out carefully, choosing the appropriate domain and condition for each. Check your work against the definition and bring your questions to the next session. See you in the next lecture.